Hello there and welcome back. We are on to our final lesson on thermodynamics and we've saved a great one for last. Today we're going to talk about entropy. So you may have heard of this concept of entropy before and how it's tied to this idea of disorder and so on. And we're going to take a little bit of a deeper dive into what it really means. So we've seen already with our talk about heat engines that our laws of thermodynamics tell us that heat is going to flow through objects from hot to cold. And it's going to do this spontaneously. And that we would never expect heat to flow in the opposite direction spontaneously. We can do work to force heat to flow from cold to hot. But if you just have a hot and cold object that's in some sort of contact, you would expect the heat to spontaneously flow in one direction. And so entropy helps us kind of understand this. The second law also states that no cyclical process can be 100% efficient. So not only do we know from conservation of energy that energy can't be created or destroyed, whenever we do work, whenever we use energy, some of it is always wasted. And so that wasted work, that inability to access that energy is related to this concept of entropy. And entropy is a kind of a funny idea. And so there's actually a few different ways to think about it. And sometimes that makes it a little bit confusing, but it is useful or important to kind of keep these different definitions of entropy or applications of entropy in our mind. So let's talk about the first way to think about it. Entropy is sometimes referred to as the disorder of a system. And this is not a bad way to start thinking about it. That if you want to measure the entropy of a system, you ask yourself, well, how ordered or disordered is it? Okay. So entropy is also, it is a state function. And by state function, we mean that's something like temperature or pressure, or internal energy, where we don't actually care how it got there. We just want to know what the entropy is at that state. So the entropy only depends on the current configuration, not how it got there. Okay, so you might think about this example here. Which is more disordered? We've got a glass of ice chips and a glass of water. Well, just looking at them, this idea of disorder, our first thought might be, well, those glass chips look like they're all like jumbled together and they're all kind of mixed matched. But in actual fact, the glass of water has much more disorder. If I was to take out all these ice chips and lay them in a line, lay them in a row, I might find a bunch of different ways that I could put those back into the glass and realize that there are a bunch of different ways, a bunch of different configurations that would fit those ice chips in the glass. And while that's true, think about the particles. So think down to the level of the particles. Since the water that's melted, or the liquid water, are free particles moving around, there are many, many, many more possible configurations for those particles. Imagine rearranging each water molecule in individual molecules one at a time. There are many different ways you could rearrange the water molecules compared to the ice chips. So we say that the water molecules are more disordered. There are more different possible configurations that they can fit in. So another way to think about, to state that same second law of thermodynamics, is that if you have like an ideal process, like an ideal heat engine, for an ideal reversible heat engine, then the change in entropy will be zero. But for any real process that involves, reality, that change in entropy is always going to be positive. So one way we write that is delta S, which S is our entropy. We say that the change in entropy must be greater than or equal to 0. So whenever we do work, whenever we use energy, the entropy of the process will increase. And so since entropy is related to how much energy there is in the system, then that process can't be 100% efficient. So that's kind of how entropy ties back to efficiency. So I want to just kind of stay on this point, this idea of configurations, because I think that's a really important point to draw. A lot of times people say, oh, entropy is just like chaos or disorder or whatever, but that doesn't really give us an idea of what we mean by that, okay? So we need to recognize that when we have a system, that system can have macrostates and microstates. And the two of them sort of depend on each other, but they're different. So the macrostate is going to be properties of, for example, the temperature. So temperature is a macrostate. And so if I have like a gas, the temperature of that gas is going to depend on some average property of the individual particles. So it depends on the average of some property. So for example, we saw like if I have a gas bouncing around in a container, we saw that if I take the temperature of the whole container, that's really just related to the average kinetic energy of the particles that are bouncing around. And I can measure the macrostate by measuring a bunch of the particles and finding their average. And then that's going to give me that idea there. So by comparison, a microstate is something that depends on the actual particles. And so the microstate is like the actual configuration of the particles within that state. So the configuration of the particles. Now, what we mean by configuration is we mean properties like position, where the particles are, or speed, energy, etc. So if you want to know the microstate of the system you're looking at, you would have to know the information about each of the individual little particles in that system. Okay, and so one way to think about this is to use the analogy of flipping a coin, right? So a coin, you can flip the coin and you can see that we've got a macrostate listed here. So the macrostate might be, for example, 10 heads and 0 tails, or 9 heads and 1 tails, and so on. That's like the zoom out overall big picture what happened. But the microstates, the number of microstates is going to be different for each one. If you flip a coin 10 times, there's only one possible microstate that will give you 10 heads out of 10. But if you were to flip a coin 10 times, there are 10 microstates that would give you 9 heads and 1 tail. And you can see here, and this makes sort of logical sense, that the most likely configuration is 5 and 5, where I've got 252 possible ways of organizing that. Now recognize that this is a pretty simple system. This is 10 coins that I'm flipping that can only be in one of 2 configurations, heads or tails, to say nothing of position or anything else. And even this, it's pretty obvious that most likely this system is going to fall into a microstate that aligns with a macrostate somewhere in the middle. Now compare that to, for example, this system here, where this is one example of a microstate, but then this is another microstate, and this is a completely other microstate. And you can imagine the number of possible microstates. You would have to list all the possible positions with all the possible speeds of all the particles in that system. There are many of them. Now, if I let these particles bounce around long enough, it is entirely possible that when I hit pause, all of those particles are all piled in the corner and nice and neatly arranged in rows, all lined up. That's possible, and if that was true, that would be a highly ordered system, but I think we know that that's very, very, very unlikely. I would not expect to sit here and in a reasonable amount of time see that microstate occur. What's much more likely is a microstate where the particles are much more randomly sort of spread. And to take that a step further, if I started with that microstate, if I started with all of my particles nice and neatly organized, I would expect very soon after that they would be all over the place. And so if you think about entropy, entropy really has to be related to energy because it helps us predict how a system will move. Just like we saw that that if I have a hot object, it will spontaneously have energy, heat energy flow to the cold object. If I have an organized state, it will spontaneously transform into a disorganized state. But the reverse is not likely to happen. And so that ties entropy both to this idea of disorder, but also to the idea of the flow of energy. And so I want to make that last point really clear because it's not necessarily obvious. Why is it that an ordered system has, say, more energy than a disordered system? Like, what does order really have to do with energy in the first place? Well, one way to think about it is this. If you have a rock at the bottom of the hill and you want to put it on top of the hill, you would have to do work. You would do work to put the rock there. And once the rock's on top of the hill, it has potential energy. It could fall back down the hill and it could do useful, arguably useful work on something. Well, the same thing is true about the order of a system. If I have a bunch of particles that are all over the place, I could in theory do work to make them more organized. I could pump them into a smaller container and make them less disordered. But if I do that and pressurize those particles, well, then they would be able to do work for me. And when I release them, they could do useful work. So the system is statistically more likely to move to a more disordered state. And I think that's one of the things about entropy that's not entirely satisfying when we first hear about it. But moving from order to disorder is an example of energy flow through a system, that we could actually use entropy potentially to do work. So an example of that would be this. Imagine I've got this system down here below. I've got two chambers connected by a valve, and I pressurize one side. So I pressurize the left side, say, to a certain pressure, and obviously it's at a certain volume. Now imagine that right in the center here, I attach some sort of turbine. So that turbine, when gas moves past it, it's going to spin the turbine, okay? So what's going to happen as I open that valve and allow the gas to flow from the left chamber to the right? Well, as the gas naturally moves from a highly ordered state to a more disordered state where it's more spread out, the gas moves from the left to the right, it's going to spin the turbine, and that spinning of the turbine is going to do useful work. So you can see that just in moving from a highly ordered state to a more disordered state, that this is giving me an idea of the amount of work that can be done. Because eventually what's going to happen? Well, eventually the particles, the gas is going to flow across, and eventually the pressure on both sides will be equalized. Now, when the pressure is equalized, there will be no net flow of particles. Of course, if I zoom in on like a microstate level, particles might still move left and right, but for every particle that moves to the right and spins the turbine one way, a particle might move to the left and spin the turbine the other way, and then I'm not going to get a net amount of energy out of this system. So essentially what's happening is once we've balanced out, or I should say once the systems become as disordered as it can be, then no more work can be done. Okay, the ability of the system to do work is finished. And this is really what entropy gives us an idea of. So entropy gives us an idea of how much energy in the system is going to be unavailable for us to do work. So entropy is the unavailability of the system, of some energy in the system to do work. I start with a highly ordered system, and as it moves to disordered, I use some of that work. I use some of that energy to do work. But once the system has reached its most disordered state, I'm no longer able to access the energy. Essentially, the pressure has equalized, and since there's no difference in the pressure, I can't get useful work out of that system. So entropy, while it's a measure of how disordered things are, it's also very much tied to how much energy there is available in a system for us to access. Okay, that is it for our lesson on entropy.